minus square root of 1 plus cosine theta over 2. All of it. All of it.
Yeah, so let's make that square root a little bit bigger so it's obvious that it's all under the square root. Cool. And so, right, the plus or minus really needs to be there, as we saw, because this formula doesn't know whether theta over 2, what quadrant it's in. So you need to figure that out independently whenever you use the half-angle identities. How does it change for sine?
1 minus cosine theta.
Nice. All right, so we have these half-angle identities. And let's now get back to where we were. So what did we do with them so far? We said, well, pi over 8, that's an angle that that's half of an angle we understand. So you can use this to compute cosine of pi over 8. How do you do it? You figure out the plus or minus by figuring out what quadrant it's in. The choice for theta you're making is pi over 4, so you plug in pi over 4 for theta. You write down that formula, you simplify, eventually get something that's relatively satisfying, I think. And then we did some more computations with that. And I think what I'd like to do today, with what time we have, is just do some more computations with these facts. For a bit, and then I want to introduce another set of trig identities called the product to sum and sum to product formulas. So, let's do these. So I think for like reasons of referencing stuff that's happened earlier, let's compute this. Let's compute the cosine of 5 pi over 12 using the half-angle identity. So I guess here's the first question. 5 pi over 12, is that half of an angle that you understand? Sure. What's it half of? Yeah, if I want this to be cosine of something divided by 2, because I want to use a half-angle identity. Well, what do you divide by 2 to get 5 pi over 12? Well, 5 pi over 6 would do the job, right? Oh, cool. So, let's see what we've got. So I guess we just need to use the formula, right? Let's write it down, we'll see what it looks like, and then we'll go from there. Equals. So, tell me what to write. By the half-angle identity, this is the same as.
Be same as, well, first of all, since we know that it's in quadrant 2, since 5 pi over 6 has a negative cosine.
Ooh, let's revisit that. I'm going to put the plus or minus in, and then we'll think about it. So, plus or minus.
1 plus cosine of 5 pi over 6.
That'd be 5 pi over 6.
That's, yes. I think my 5 was just really bad. Divide by 2, and square root it. Cool. Yeah, so let's think about this plus or minus. So which angle did you just tell me was in a particular quadrant?
5 pi over 6.
Cool. So 5 pi over 6, this angle is in quadrant 2. I agree with that. But I want 5 pi over 12. So when you want to think about like whether this thing's going to work out to be positive or negative, since I want to compute cosine of 5 pi over 12, it's this angle whose quadrantness I care about.
So basically you reflected on the origin since you're doubling it?
Not reflecting over the origin. Let's draw a picture. So you saw 5 pi over 6 is like there-ish. Maybe that's too extreme. Here's 5 pi over 6. Half of that is going to be half of this size. So it'll be like there-ish. And I guess this also tells us like what quadrant it looks like it's in.
Looks like 1.
Looks like quadrant 1. And let's also see that just by inequalities. Right, our right angle is pi over 2. 5 pi over 6 is less than pi over 2? Yeah, because,
over 12 is.
yes. 5 pi over 12 is less than pi over 2. That's less than pi over 2. Yeah, so that should be in quadrant 1. So, plus or minus?
Plus.
Plus. Awesome. So there's the subtlety. And this is like a mistake I see a lot on things like exams when people use the half-angle identities. You care about whether that sucker is in quadrant 1 or quadrant 2. All right, but now that we have that being plus, now we can just like proceed in not an easy way, but a way that should feel automatic. Right, like you look at that, you just need to evaluate it now. So let's take one step at a time. What's the cosine of 5 pi over 6?
Negative root 3 over 2.
I hear a negative root 3 over 2. Do I hear a second? Nice, yeah. So, oh, maybe this is a good time to ask this. How many people are planning on having a units algorithm on that exam that's coming up? Yeah, cool. Maybe you think it's not totally necessary because you're also allowed a calculator. And if you think of the units algo as being like a computational aid, you can do the computations via machine, but it's nice to be able to like see it. I'd say don't bring the units algo that's like the one that I handed out that's in your notes because that's like way too big. And you should like keep that. Because I'm not going to give back whatever note sheet you fill out. Anyway, what did you say this thing was? So square root of 1 plus, what's cosine 5 pi over 6?
Negative root 3 over 2.
And then all that over 2. All right, neato. And this looks an awful lot like the thing that we simplified yesterday, at the top of the page. What do you do to simplify this? Yeah.
The negative root 3 over 2, since that's all being divided by 2, that turns into negative root 3 over 4. And then the 1 becomes 1/2. So it's 1/2 plus negative root 3 over 4.
Works for me. All right, what next? Say that right.
Common denominator.
Get a common denominator. And what is that common denominator?
4.
4. All right, so 1/2 is going to be 2 over 4. So that's big square root 2 minus root 3 over 4. All right, nice. Are there any possible square factors or divisors under that square root?
Yep, there is 4. Take out as 2.
Yeah, cool. Oh, shoot. I was planning on interjecting an asinine joke comment at the end of that response saying, no, there's only one perfect square under that square root. And I failed to do that. It would have been a funny joke. It's better if it's explained though, right? Neato. Cool. So we get the square root of 2 minus the square root of 3 all over 2. Does that computation feel pretty okay? Do you remember doing this computing the same thing earlier though, using a different technique? Maybe say angle addition? In fact, go back to like the bit of the notes where you did this using angle addition. What did we get earlier using angle addition? Maybe I'm going to use the top of the next page. So what do we have right now? Cosine 5 pi over 12 is square root 2 minus square root 3 all over 2.
Here's what you're ready.
Well, I'm just writing down what we just got.
Oh, okay.
That's by half angle identity. But if we did the same thing using angle addition, because we did this using angle addition also, right? What did we get when we used angle addition to do it?
Square root 6 minus square root 2 over 4.
Well, those don't look the same, do they? I guess they better be the same. And the reason I'm lingering on this is for like 2 reasons. How many people here are calculator users today? Yeah, if you got one, take it out. Compute one side or the other. Let me know what decimal approximation you get for, I guess, either of these. Hopefully they're the same. Are they the same? Oh, that's neat. So the reason I'm also lingering on this is because of something that like I want to mention in passing that isn't part of like the course content. It's kind of weird these two are the same, right? It's suggestive that maybe there's some like secret identity about how square roots behave when there are like sums and differences of square roots under the square root. Maybe think on that a bit. Is there something deep going on there? Cool. So, let's see. And maybe I'll even check this so like, we're gonna do like lots of review next time. How do people feel like they benefit from doing like another angle addition example explicitly right now? Oh cool, then let's do it. I know we just said what cosine of 5 pi over 6 is right there, but let's remember how to get that. So if you want to compute cosine 5 pi over 6 using angle addition,
We can't see.
if you want to compute cosine 5 pi over 12 via angle addition, well, I need to find 2 angles that add up to be 5 pi over 12. Or subtract. Subtraction would be fine too. Can you think of any 2 viable candidates? Well, those of you who like just recently looked at that previous page definitely have some, but let's just try to come up with some.
You wrote 5 pi over 12, or you wrote 5 pi over 2.
Thank you. Hopefully I said 12. Who knows? So I need to find 2 things that add up to 5 pi over 12. And are also things whose trig functions you know. So tell me some things that might add up to 5 pi over 12. In fact, ideally it's slightly wrong. Yeah.
Pi over 6 over 2.
Ooh, pi over 6. And what else?
Or I said pi over 6 over 2, so isn't that half of pi over 12?
That is half of pi, that will give pi over 12. But I want to do angle addition. Like we've already done 5 pi over 12 using half angle. I guess you could do pi over 12 using half angles too. Maybe that's worthwhile to do. But like I want to stay on this, so I want to find things that add to be that. So if you want to get off topic for a bit, it's a very loud soda pop. Anyway. Give me 2 things that add together to be 5 pi over 12. They don't even have to be right. Just 2 things that might add to get a 12 in the denominator.
Pi over 4 and pi over 6.
I hear a pi over 4 and a pi over 6? That seems hopeful. Because at the very least, what's the common denominator between the 4 and the 6? 12. Awesome. And I wrote down 12 because I was about to say 12. And did you say plus or minus?
Plus.
Cool. Let's do plus. And I guess if you wanted to check that, well, this would become like 3 pi over 12 and another 2 pi over 12. Yeah, that checks out. So if you want cosine of 5 pi over 12, well, you know what to write. Ooh. Let's see if we can remember the angle addition formula for cosine from memory. So cosine of 5 pi over 12, this should be the cosine of pi over 4 plus pi over 6. Angle addition for cosine is
Cosine of pi over 4 times cosine of pi over 6 minus sine of pi over 4 sine of pi over 6.
nice. Yeah. Angle addition for cosine says multiply the cosines, multiply by the sines, and then take the difference. All right, and all those things are like things we know, right? What's the cosine of pi over 4?
Root 2 over 2.
Root 2 over 2. Cosine pi over 6?
Then square root 3 over 2.
Ooh, well, if there was a question at the end, then like, do you have your unit circle on you?
I don't know where it is.
No, you should probably have one of those by the time the exam rolls around.
Yeah.
Yeah, it's root 3 over 2. Ooh, well, here's like a good way to just like visually see it. So like, those are the 3 angles you see in quadrant 1. The smallest one's pi over 6, the middlest one's pi over 4, the biggest one's pi over 3. And you also know that the 3 numbers you see are 1/2, root 2 over 2, and root 3 over 2. That point has the biggest x value of those 3 points, right? So you just need to know which is biggest, root 3 over 2, root 2 over 2, or 1 over 2. And yeah, it's root 3 over 2. So you can reinvent that on the spot if you just like know what numbers go in, and then you just need to put them in order. Anyway, minus sine pi over 4.
Square root.
2 over 2.
Sine pi over 6. Nice, because that's now, that y value is the littlest y value in quadrant 1. Oh, nice. So now just multiply it together. Root 2, root 3 is root 6. Root 2, root 1 is root 2. Denominator is 4, denominator is 4. Yeah, awesome. That feel pretty good? While that was happening, did anyone decide to just go off topic and just do this computation instead? No shame if you did. No shame if you didn't. Good. All right. So, it's 20 minutes in. Well, I think we have time to do this then. Let's proceed and tell like a bit of a story that you can tell once you have half angles. So let's start with this. We computed this, I think, on the previous page. What's the cosine of pi over 8? Just flip back to the previous
Square root
page.
of 2 plus, no, it's the square root of 2 plus the square root of 2 divided by 2.
Nice. Where like the parentheses that you never actually pronounce are like pretty important in what order they show up in. But like, yeah, that's right. Well, if we now have cosine of pi over 8 now, let's use that to compute cosine of pi over 16. Because pi over 16 is pi over 8 over 2. Shall we? Let's do it. All right, so I'm going to use the half angle identity again. And I guess there's what I'm going to use for the theta in the half angle identity. Yes, the variable name that's on the board is theta. And let's deal with quadrant at the same time. Pi over 16, what quadrant is that in? Nice. So the plus or minus in the half angle formula is going to be a plus. So this is going to be plus big square root 1 plus cosine of pi over 8 all over 2. Did I do anything wrong? Okay. Ooh, all right. So now, let's proceed. Let's start by subbing in the thing that we know cosine of pi over 8 is. So it's the square root of 1 plus, what's cosine pi over 8?
Square root of 2 plus square root of 2 over 2.
Nice. Big square root of 2 plus square root of 2 all over 2. Then there's an even bigger square root around everything. All that divided by 2 still under the square root. All right? And let's just see if we can tell the same story again. So earlier we like distributed the division onto each of the sum ends. Can we still do that? Yeah, it's still just two things added together. So big square root of 1/2 plus the square root of 2 plus the square root of 2 all over 2 and then divide by 2 again. Oh, cool. Does this actually look like it's falling into place kind of similarly? Yeah, so let's just keep on going. So the next thing we did is we like took those two fractions, we got a common denominator. What's the common denominator between those two fractions? 4. Oh, in fact, that's the same as last time. Equals, still big square root, 2 plus the square root of 2 plus the square root of 2 all over 4. Any further simplification? Same as last time? Oh, neat. That's kind of like an interesting looking number. Big square root 2 plus the big square root of 2 plus the square root of 2 all over 2. And what do you think? Do you see like a pattern emerging for what maybe is going to happen if I do it again?
You keep nesting square roots within each other?
I think there's going to be some nesting square roots. So let's maybe even make a conjecture. Let's not check this conjecture. Conjecture is fancy mathematical word for a thing that I think is true, but don't have like a proof of. I don't know it's true. Sometimes it's used also for just something that you like really want to be true. So let's divide by 2 again. That's going to give us cosine of pi over 32. What do you think that should be, just noticing this pattern?
Like the square root of 2 plus the square root of 2 plus the square root of 2, 2 plus the square root of 2.
That many?
I think so.
Something like that.
Can be 4 square roots.
Yeah, and all like nested like that. All right. Here's a thing for you to do on your own time. Check that. And like you know how to check it. That's an angle you know divided by 2. Apply the half angle formula. See what happens. Nice. All right. So with that being done, I want to move on from half angles, and with like the 15 minutes I have left before my alarm's going to go off, let's spend a little bit of time on one last topic.
My calculator can't do more than 3 square roots nested in each other.
Oh, weird. That can't be. Oh.
I can do 4.
All right, what'd you get?
Oh, I wasn't actually doing it.
Oh, okay.
Checking how many I can do.
They're the same.
Okay, well that's good. At least the calculator gives the same decimal approximations. They might just be like within like 1 over 10 to the 10th of each other, and the calculator won't tell you that. But surely they are actually equal.
Okay, no, I got it wrong. I was trying to put it in as a fraction since my calculator can. But if I just do it as as everything divided by 2 instead of translator. I think it's because the numbers are getting too small to display.
Oh, that could be. Yeah. Eventually, I'm gonna like get memory issues on the calculators. So here is. Sometimes in life you encounter a situation where you see multiplication going on. And multiplication isn't what you want to see going on. Like addition would be easier. So let's try to develop a rule that will let us turn products of trig functions into sums of trig functions instead. And then we'll see what that's going to let us do. And in order to get this rule, here is the logic I'm going to follow. This might seem totally unmotivated now, but take two numbers a and b. Let's compute cosine a minus b plus the cosine of a plus b with some color coding, and see what we get. What does the angle addition formula say for cosine of a minus b?
Cosine A, cosine B, no, sine A times
I agree. It's one or the other. Which one?
Minus.
Minus, yeah.
Wait, no, it's plus. Wait, no, cosine is the
Yeah, the blue one I want to do, oh no. I want to do minus for the blue one. So this one should be a plus. Minus becomes a plus when you do angle addition. And then the same thing for cosine of a plus b. That's going to become cosine a, cosine b, minus sine a, sine b. And an interesting thing's about to happen from the point of view of that, like, almost an error that just happened. What do you get when you add those together? I've stacked them to make it easier to add.
Two cosine A, cosine B.
Yeah, cool. I see a cos A, cos B plus cos A, cos B. Those stack to give me 2 cosine A, cosine B. And then I see sine A, sine B minus sine A, sine B. Oh, those cancel. Oh, so notice if I had like accidentally made that sine error on both of them, they would have just canceled out anyway, so. Anyway, so let's take a look at that. That means cosine of A minus B plus the cosine of A plus B is equal to 2 cosine A cosine B. Oh, well, if I then wanted a formula for cosine A cosine B out of that, what do I need to do to the thing at the top of the page to get the thing that's going to go in that box?
divide by 2.
Divide by 2. So let's divide that by 2, put that in this box. So apparently cosine A cosine B is equal to half of cosine of A minus B plus cosine A plus B. And I've already done the divide by 2 because I multiplied by half. So this says if I give you any two angles, and you see the product of those two angles in some cosines, you don't need to see a product of two angles. It's just half of the sum between those two cosine values. And for one like slightly contrived example of what this lets you do, let's imagine this situation. All right, like, let's try to compute cosine 5 pi over 12 times cosine of pi over 12 and see what happens. And maybe I'll acknowledge one thing first. Could we just directly compute cosine 5 pi over 12? Yeah, in fact, we did it. It's on a previous page. Could we also compute cosine of pi over 12? Yeah, probably. It's certainly half of an angle you know. It's also a sum or difference of two angles you know. But let's not do that. Let's use this formula instead. It'll be a little easier. So let's use this formula. Is that a product of two cosines? Yep. So what should I use for A?
Pi over 12.
Sounds good to me. Let's have that take the value, have the role of A in the formula. And I guess the other one's going to be B. So if you do that, let's see what we get. I see a 1/2 cosine of A minus B. So that's 5 pi over 12 minus pi over 12. Let's make that 5 a little bit better. Plus cosine of 5 pi over 12 plus pi over 12. Cool. So far that doesn't seem like that impressive, right? There's not much there. Let's see what we can do. What's 5 pi over 12 minus pi over 12?
4 pi over 12 or pi over 3.
Nice. I like both of those. So I see 1/2 cosine of, I'll write the 4 pi over 12. If you notice immediately that that's pi over 3, then go for it. Plus cosine of 5 pi over 12 plus pi over 12.
Pi over 2.
Pi over 2. I'm going to write the 6 pi over 12 just to have the steps spread out. Yeah, so both of those things inside the parentheses simplify now. I see 1/2 cosine pi over 3 plus cosine pi over 2. Oh, cool. Are both of those angles that you understand? Yeah, great. What's the cosine pi over 3?
1/2.
1/2. by looking at your unit circle. So I see 1/2 plus cosine pi over 2. 0. Neato. How many people at this point would still need to look at your unit circle to tell me cosine of pi over 2 is 0? Nice. You don't get past that though. Like, picture that on the unit circle in your head. It's a right angle, so like. Alright, like you're allowed the note sheet on the exam, but. Nice. Oh, cool. So like you can't compute these two, well, you can compute these two trig values on the nose exactly. But the product to sum formula lets you turn that into something that's easier to directly compute. And you just get a quarter. That feel pretty good? And let's see, I think instead of, let's linger a bit on like what else we could do. So maybe it's also nice to have a product to sum formula for sine. And let's maybe just think about how you would get the thing, and then we'll write something down. So to get the product to sum, the product to sum for cosine, we use that in the sum formula for cosine. You see a cosine times cosine. Between the sum formula for cosine and the sum formula for sine, which one has a sine times sine in it? Still cosine. So let's use angle addition for cosine again to do this. So I guess like, there's what we have. How would you need to change this to get the sine times sine to show up instead of cancel?
We need to subtract.
Yeah. If that were a minus instead, then that would be a minus and these would cancel. That would be a minus minus, so it would sum. You get 2 sine A sine B. So, cosine A minus B minus cosine A plus B is 2 sine A sine B. So sine A sine B must be 1/2 cosine of A minus B plus, nope, minus cosine of A plus B. Let's make that minus chunkier. Just a minus sign in between. Why do I ever use a non-erasable pen? Cool. And let's see. If I wanted something that has a sine and a cosine, well, which one has a sine and a cosine in it? Certainly not the sum formula for cosine.
Sine.
Sine should do. And in fact, maybe this tells you what you're going to wind up with. Product to sum for cosine tells you that this is 1/2 sine. I also need to replace that cartridge. A minus B plus the sine of A plus B. Cool. So whenever you see a product of trig functions, you can write it as a sum. And with 5 minutes left, maybe I'll acknowledge that there are product to sum formulas. But instead, I think I want to jump right on over to the so-called power reduction rules. So here's a neat thing about trig functions. If you see like big powers of trig functions, well, a power of trig function is like a product of trig functions, right? Cosine squared is cosine times cosine. So I should be able to write this as just a sum of a bunch of trig functions. So this means you never have to see an exponent on a trig function unless you like want to. So cosine squared of x, that is cosine x times cosine x. Ooh. By the product to sum formula, what is that the same as? And maybe here's what I'll do. I'll let you stay on this page. I'll flip back to what the product to sum formula says. And then I'll go to the board. And then I'll go back to the paper.
Would it just be half cosine x minus b plus cosine x plus, or x minus x, x plus x?
Cool, I like that because I'm going to use that for A, that for B, and then minus or plus.
Plus
Cosine of,
x plus x.
I like that. And that like kind of obviously simplifies now that it's written down. What's x minus x? 0. What's cosine of 0?
1.
And x plus x is?
2x.
Oh, there's a handy formula. So, whenever you see, now I'm going to go back to like the page in the notes. Cosine squared of x, that's the same as cosine x, is the same as 1/2 cosine of x minus x plus cosine of x plus x is the same as half of 1 plus cosine of 2x. So whenever you see a cosine squared, you don't need to see a cosine squared. Instead, you can say, I just want to see that thing with a 2 inside of the parentheses instead. And sometimes that's like easier to walk with. And I want to do one reasonably explicit example of using that. So let's suppose I asked you to solve that equation. Cosine squared of x equals 1/3. So let's acknowledge first that you already know one path to a solution. You could take a square root, and you'd get a plus or minus in front of the square root of a thought. Then you do inverse cosine, and then do the stuff to get all the solutions. But maybe it's annoying to see that plus or minus. So let's take a strategy that doesn't need us to take a square root, so we don't see the plus or minus. Let's use this power reduction formula. Instead of solving cosine squared equals a thought, let's solve 1/2 1 plus cosine 2x equals a third. Does that also look like something you know how to solve? Yeah, I think so. Let's talk through the process of solving it. What do you do first? Yeah.
Distribute out the 1/2.
Did you say distribute or?
Distribute, yeah.
Oh, cool. Yeah, I like that. 1/2 plus 1/2 cosine of 2x equals 1/3. How many people would rather have multiplied both sides by 2? Do it. Both fine choices. All right, that's where we are now. What should I do next? Subtract 1/2. And again, if you were following a different strategy, then you have a different next step. 1/2 cosine of 2x is 1/3 minus 1/2, which in the interest of speed is just 1/6, right? All right? Cool. So now what do you do next to get rid of the 1/2? Yeah, get that onto the other side. Let's multiply it by 2. Cosine of 2x is 2/6, also known as a third.
Shouldn't it be negative, since you did 1/3 minus 1/2?
Ooh. True fact. Yes. When I say I'm doing things in the interest of speed, I should still be correct. Oh, nice. And this is a situation where that, like, you know what to do. You find, like, the first solution, which is, what's the primary solution to this equation?
Cosine inverse of negative 1/3.
Nice. What's the secondary solution?
Negative cosine inverse of negative 1/3.
Nice. And in order to account for periodicity, what do you have to do still?
Add 2πk.
Yeah. So that was a nice, like, blast from the past of things that you remember doing. Oh, cool. But I still need to get x on its own, so what do I still need to do?
Divide by 2.
Nice. So x is either, well, let's just put the plus or minus out front. 1/2 cosine inverse of negative 1/3 plus divide this by 2 is pi. Okay. Groovy. That feel pretty all right? So here's one use of the power reduction formula, is you can use it to reduce powers. If you don't want to see a square, you don't have to. Nice. And what I'm going to do now is I'm going to start distributing the quantity emails. Don't start filling these out until I'm not in the room, because I'm not allowed to be in the room while you're doing it. Once you fill them out, go ahead and throw them in this manila envelope, and you'll bring them up. If you go up to the 5th floor,